All right, guys, we're going to start on the second lecture for Chapter 9, and this is the multiple linear regression chapter. We're looking at a continuous response variable with more than one predictor variables. Usually the predictor variables are continuous, but there can be some that are categorical, and the chapter talks a little bit about that. And you are preparing to do group and individual homeworks for Chapter 9 that have been posted on Canvas. You're welcome to ask us questions about them as you go along. So I'm going to start on the slide that goes with this, Chapter 9 Multiple Linear Regression. It's a Google Docs slide, and I'm starting on slide number 11. We already talked about the earlier ones, and this is about strategies for multiple linear regression. So I'm going to go and look at it. It's focused on, so we'll look at this particular display in the book. It's on the slide and it's in the book. Here it is in the book. Woo, yay. All right, so this is great because it kind of gives us a process for walking through how to tackle these multiple linear regression problems. So the first thing, in a lot of cases, like in a case study or an exam, you might not even know you're dealing with a multiple linear regression situation. So the way you know that that's what's going on is you have a continuous response variable and you think that more than one thing is needed to predict it. So your first step is you figure out what the question is. What are the scientists trying to figure out? And you try to understand what the purpose of the model is. And we'll look a little bit more in depth at different purposes of models. But you might be doing regressions for different reasons. And the reason you're doing it will have an impact on how you proceed with selecting the best models, whether you're going to interpret the slopes or a confidence interval around the line, whether you're trying to make a complicated model that explains quite a lot of the variance because predicting things as perfectly as possible is really your mission, or whether you're really trying to understand how one thing causes another thing and you only really want predictors in there that make sense scientifically, even if it doesn't explain as much of the response variable. So step one is always figuring out what the heck are they talking about and what is the point of doing this. So that's the preliminaries. Your next step is to explore the data using graphical tools, and we will focus on doing this for the gestation example coming up soon. So really, one of the key assumptions of linear regression, multiple linear regression or simple linear regression, is that the variables are linearly related to each other. And if you have a bunch of variables, that means you need to look at a bunch of plots and see whether the variables are actually linearly related to each other and whether they really do have fairly equal variance, whether those assumptions are reasonable. So you should be looking at the plots. Then you're going to make a model. So you're going to do like LM and like the response variable, tilde, the predictor variables. That's where you're making the model. You're going to check the model. You're going to look at the assumption of equal variance along the line. And sometimes you will notice that some of the terms can be dropped, like that are not significant, or especially interactions that are not significant. So you'll take those out of the model and rerun it as a simpler model. Or sometimes you'll look at it and you'll realize that actually the variance is not equal and maybe you need a squared term or you need to reassess like a log transform. So at this point you may end up dropping some terms, adding a log transform, tweaking the variables in the model to make sure that they meet the assumptions. Once you have a good model and you feel satisfied with it, step 4 is you're going to make inference about the model. So inference is when you take the model and you use that to make more general statements. Like you might make inference about the slope by saying like, for every 1 unit increase in this predictor, there's an associated X or whatever your coefficient is, unit increase in the response. Interestingly, if you have several predictors in a model and you want to make inference, and like say you're making inference about, you're like thinking about the intensity and the timing with the meadow foam example that we just talked about. If you want to make inference about the timing, you need to be talking about the same level of intensity. Or if you want to make inference about the intensity, you'd say, holding time constant, the intensity does this. So anytime you have a multiple linear regression, when you're looking at one of the slopes, you're holding the other things all constant so that you don't like have to look at multiple moving parts all at once. So you're making your inference. You might be also looking at confidence intervals around the line, like we did for the meat packing example. We were looking at prediction intervals. That same basic idea could happen in a multiple linear regression context. And then the last step is communicating the results, and you'll have a lot of practice doing this on your homework and on your case study. So this is the part where you make a beautiful, lovely graph with very well-labeled axes, and you put your conclusions in the terms of the original question. So you don't just say like reject null hypothesis. You use the words that the scientists used to ask the question that made you want to do the regression. So that's the last step. So we have kind of looked at all the things in this display, which is also on the slide. If you have any questions about those, please feel free to send us an email. We'll be happy to tackle those. Let's look at slide 12. I have a few more details. You kind of have three main scenarios that you're interested in doing multiple linear regression. In the meadow foam example, you only had a couple predictor variables. You had two, and you were interested in modeling both of them. So that's cool. You can model both of them at once. It's not super complicated. You have other cases where you might have a whole bunch of potential predictors. For example, maybe I'm interested in knowing where sagebrush grows. And potential predictors might be like the kind of soil and also minimum April temperature and how much rainfall falls in the winter and how long the snow melts and whether there's pronghorn that eat them. And you could have like dozens of potential predictor variables. Anytime you're pulling climate into a model, you could have like August temperature, December temperature, September minimum temperature. Now you're in a case where like there's a whole bunch of predictors and you need to figure out which ones to use because you're not going to make a model with all of them. It would be like way too much. So chapter 12 really dives into how do you pick them if you have a whole bunch of them. And then the last situation might be that you're really only interested in one potential predictor, but you really do need to account for other possible explanations. This is likely to come up in your next case study. So the thing you might be interested in, whether men get paid more than women. But to really properly model that, you need to account for years of experience, expertise in the subject, maybe the field they're in, like maybe some fields get paid more than others and that's something you need to account for. Maybe you need to account for their job performance or their education level. So you might have a situation where you're really interested in one particular thing, but you have to account for all these other things. Another example you might see is the case of whether air quality affects people's mortality rates. And there are a lot of other things that affect people's mortality rates, like their socioeconomic status and whether they live in a place that has high mortality rates for whatever reason, their health, all sorts of things. So if you wanted to really conclusively show that air quality affected mortality rates, you would want to take all of those other things into account. So this third use of regression is for when you want to take a bunch of other things into account so that you can more conclusively test this last variable that you're really most interested in. All right, so let's look at this gestation example. So in this example, it's one of those cases where you're actually trying to take a particular thing into account. So we're looking at all these mammals. We want to know about brain size and whether brain size is associated with other variables like how many babies they have and how long they gestate their babies after you account for body size. Like we know that things that are bigger have a bigger brain because like they're bigger and they have more space to hold a big brain. So you're accounting for body size, and then you're interested in whether these other variables can affect brain size. So I looked at the data set, and here's the code is posted on Canvas. The data set is in the book on page 241, and the first animal in it is a quokka. I'd never heard of one. It's like this super cute little wallaby type thing. There's a picture of it on the slide. Okay, so we're gonna model brain size related to these other variables. And the first thing to do is to look at a scatter plot of all of them. So let's go to slide 14. This is called a scatter plot matrix. There's like way more plots on here than you should look at. Don't look at all of them. So start by looking at brain size. We're interested in brain size being the response variable. So we're interested in the graph where that's along the vertical axis. So really we're only looking along the top row of these plots. If we look at how brain size relates to body size, that plot's kind of ugly. Man, all the points are like clustered over in the bottom left, and there's like this point like way up in right corner Timbuktu land. It's not very linear. I don't love it. If you look at how brain size relates to litter, that looks okay. Maybe there's an equal variance issue on the bottom end of that, but like at least the points are kind of scattered along a line. If we look at how brain size relates to gestation, it looks like you have a sort of funnel shape, like it's sort of linear, but there's definitely an equal variance problem there. The points are a lot closer to the line in the bottom part of the plot and further away from the line in the top part of the plot. So when I look at this, I think, gosh, I'm going to make a terrible linear model if I just use these. I really need to think about some transformations, particularly with body size and gestation. So I'm going to try making the same set of plots after log transforming body size and gestation. So that is on slide 15. And if you check out, I also transformed brain. Cool. So you do these log transforms, and it's great. You look along that top line of plots, and all of them have like pretty much linear relationships. This is fantastic. This means I can use multiple linear regression, and I'm probably going to meet my assumptions. So, step 1 done. Cool. I do want to look a little bit more carefully at some of these points that look like maybe they're outliers. So let's go to slide 16. I'm zooming in on this relationship between log brain size and log body. And this point up in the upper right is the African elephant. And it's like kind of an outlier maybe. It's like off away from the other points. And I kind of need to decide whether I feel like it's going to change the slope of the line very much. If it was off away from the other points and it was like way higher than where all the other points would go in a line, or way lower, then it would like pull the slope of the line up or down. And that could really affect my results, and I would worry about that. And try to think about like maybe African elephants like shouldn't be part of my population, or maybe I should report the results with and without African elephants. But in this particular example, I'm really not that uptight about the African elephants because they're like right along where the line would go. So they're probably not going to affect my results very much. But at this point, this is where I would be starting to look at outliers and think, how are they going to affect my results? And I'm cool with the African elephants. I'm going to keep them. So let's go on to slide 17. We just do our model. So our formula here is the log brain size is modeled by the log body size plus the litter plus the log gestation. We can see the rows from this analysis. All 3 predictors are statistically significant. The model explains about 95% of the variability in log brain size, which is cool. It's a good model. Let's see, anything else? So I did account for body size. That was like well, duh, we know brain size is related to body size 1. And even after that was included in the model, the other 2 were significant. So that's good. We should check our residuals. So the next slide, slide 18, is our residual plot. We're looking to see whether the equal variance assumption is met. It's not perfect. You can see the labeled numbers are the points that are like maybe outliers, but it's reasonable. It's okay. So I would proceed with this model and say it's all right. We can get confidence intervals. Here on slide 19 is the confidence intervals for the slopes and the intercept. And you, just like for simple linear regression, how you needed to account for the log transformation to interpret the slopes, the same is true here. So these are on, well, the body and the log gestation are on a log-log scale, and the litter is just on a log regular scale. So you need to go back to the chapter on simple linear regression to remind yourself of how to interpret these. So they're all going to be on the scale of a multiplicative scale. And we get the confidence intervals for them here, and you would back transform them just like you did before. Okay, and then we go on to slide number 20. And this is also important because the specific question the researchers asked was, which, if any, variables are associated with brain size after accounting for body size? So we need a way of formally testing whether the litter and gestation, both together, are significant when you're keeping body in the model. And the output we just looked at tested litter size separately from gestation, which is not really actually what the research question asked for. It asked for them to be tested both together. So this slide 20, looks at an extra sum of squares F test to test this question. So it compares the more complex model, my LM2, has body, litter, and gestation all in it. And my reduced model, this is a simpler model, my LM red, just has brain and body. So if litter and gestation don't really make the model that much better, I should get a non-significant p-value. If they are important for predicting brain size after accounting for body size, then I should get a small p-value. So I run that. This last line is my ANOVA running the linear model, the simple versus the complex model. And then this last part is I get from that a p-value of 5.9 times 10 to the negative 9, which is very strong evidence that indeed litter and gestation are important after accounting for body size. So that is the end of this second example from Chapter 9. I think we've gotten the main ideas from Chapter 9 under control, and you should be ready to tackle your homework on this topic. Again, please feel free to email or discuss or request a time for a video chat with either Dr. Chen or I. We really want to help you get through this last bit of the course. You should expect coming up a case study that focuses on multiple linear regression. Next week, Dr. Chen will start discussing Chapter 10, and there will be a new homework about Chapter 10. So beware that that's coming up next. And I hope you're all washing your hands and having a fabulous time hanging out all by yourselves in your houses. I kind of miss seeing your faces. But I'll talk to you again later. Bye.